started if we want to hit record. Perfect timing. Thank you. I am, of course, Hannah Hellman. I am the communications person for Eclipse Megamovie. You've heard from me in one form or another, be it the listserv emails or bugging you for information or asking you questions. Um, we'll really quickly go over the agenda for today as soon as I pull it up from my email where it exists. That's so sweet. Um, Well, today Laura's going to be talking to us about the Helio Viewer tool, a NASA tool that she and Troy had the chance to play with a little bit, and the kinds of pictures and like visualizations and things that you can make with it are just out of this world. Haha. Um, Troy will talk a little bit about the Kaggle competition, and I think I'll start us off by talking about volunteer appreciation, Laura. Does that sound good? Okay. Um, if you have not already gotten an email from me, asking you about your address or the name that you would like to have it as it appears on like a certificate or that kind of thing. You may in the future. So we have plans for our volunteer appreciation. And the first part of the plan was a small gift that we are sending out. We tried to go by as you responded on your survey, if you were able to meet all of our gold standard requirements. If you're able even to meet like 50% of them, you should have a gift headed your way. But, I'm also reading the comments and it says, if I see something that says, well, I really tried and I did this setup and just things just went wrong, then, you'll also have a gift headed your way. Really, most of you should have one. But the second phase of our recognition is coming in the forms of these certificates that Aurora, who does all of our graphic design, such as the graphic in Laura's background, has created a beautiful certificate for everybody. So if any of you are international and we are not able to ship it to you, we can send you a PDF and you should still be able to get it that way. Um, Outside of that, we are also continuing to do volunteer highlights. I submitted yours, so I'll let you know as soon as it pops up. And if any of you, if any of you are interested in, being featured in such a highlight as we've had Nasmus Nasir or Nastronomy featured in the past, reach out. Let me know. We'll work together. We'll get your story put out there. So keep an eye on your mailbox. You should have either a small gift or a certificate or both headed your way. I think that's everything for volunteer appreciation. Any questions I can answer? Now is a good time, I think.
Hannah,
Yeah.
um, I'd be happy to actually personally foot the forwarding Matthias in Austria or Germany,
Hmm.
his certificate to him. So if you want to stick it
Well,
in
thank
the
you,
same
he.
envelope, and I'm more than happy to. I know why you can't do it because it's National Science Foundation funding. No comments. Also, they're much nicer than some other organizations,
hmm
and
hmm
uh, but he has been such a delight to work with that
Oh, that's
I'm
so
happy
sweet.
to, yeah.
I think
And the poor guy,
he.
his baggage went off to weird
Oh.
places.
Oh
You
no.
remember that, right?
I do. I do.
Yeah.
Yes, that was so stressful for him. Oh my gosh.
Yes.
I think he has given me a forwarding address that is in the States, but if not, I'll talk to Laura and we'll talk to you, he. Okay, thank you. That's a really generous offer.
I have a
Awesome.
question.
Yeah, please.
I am to assume that the lens cleaning kit was not the consolation prize.
Oh, no, it's not a consolation prize at all. That is the
Oh,
thank you gift.
and
That's
I just
the
I
the
just
small gift. Yeah.
I just threw up my Aurora photo in my background.
Ooh, look at the green. Wow.
Norway 2013.
Oh, how cool. That's beautiful. Yeah, so the lens cleaning kit is the small gift, but it's not the commemorable gift. It is that's the certificate that we're preparing, but we're customizing each of them, so it takes a little longer than just shipping out the small thank you. Awesome. Good question. Any others? Okay. Troy, are you ready?
I suppose as ready as I'll ever be.
As ready as we deserve.
So yeah, I suppose a brief update. Over the past couple of weeks, we've been working on getting all of the bits and bobs together to get the Kaggle competition ready. And that is just about ready. There's one or two more boxes that need to be checked off. Um, Something to consider for those of you interested in the Kaggle competition. The the labeled data set is relatively small, and so our expectations of results uh, are in align with that. Um, Beyond that, do we have a date that that is starting, or are we saying soon?
Well, we'll get, our goal is to have it out tomorrow, right? So that's still our
Yes.
goal. Yeah.
Okay.
Um, so tomorrow's still the date, October 1st. And then we'll be advertising it, and um, yeah.
Yes. So once all the boxes are checked and I can press the big green button, I will likely pass some information over to Hannah, and Hannah will blast out some emails to let everybody know what's going on. Um, I think that's all from me on the Kaggle competition. Um, Sort of just a general update on data. We're working with a professor here at the university. We may have talked about this in a previous meeting, but we're going to talk about it again. Um, we're working with a professor for his one of his computer vision classes. We're providing him information about a lot of the images that were taken in the 2024 Eclipse, and he's using them for essentially the entire latter half of his class for them to do their final projects on. Um, Detecting uh, offset rotations of where the image should be rotated to and how far it is off. Um, so we're working on getting those labeled, and those should be to him, and his class should be starting that in 2 weeks, I believe, 2 to 3 weeks.
And I think he even asked Laura to come and speak to the class about Eclipse Megamovie and um, the kinds of possibilities of the intersection of coding and science.
Yes, I believe Laura and I will be going and doing that.
Yep. Yep. So Troy and I will do that. Um, so I think also there was a question kind of when is our video coming out? And we the earliest would be December, and that's if we can get everything aligned. And so as we discussed before the eclipse, the alignment was always a question. We had Regulus to align to. Um, of course, even with Regulus, there was atmospheric effects, and so that move the apparent location of Regulus into another part of the sky. I mean, not by a lot, but by some quarter of a degree or so, or even less than that, but still enough that it caused some challenges for creating the very first, really the comprehensive Megamovie that was released, I think 9 months after we got it. So we're using a lot of that same code that we had, and we're trying to align using the prominence that I think all of us saw who got to actually see the eclipse. So there was that little orange prominence that looked kind of like a tongue. And so, but of course, the way the moon comes into the sun and covers it, there it covered even as it's fully covering the photosphere, and you can see the chromosphere and the corona. It does cover that in some of the images, and so we can't use it for all the images. So that's why we're trying to have this machine learning to help us orient when we don't have that as a thing we can hang on to. And just we just got, so some of you, it seems like forever, but this is the pace of science. It takes forever, seemingly. And so we just got the data from Berkeley, so it was at a shared point at Berkeley, and we left it open because some volunteers couldn't get their data uploaded until June. And in fact, we had one volunteer. We left the upload open till July 3rd, and actually someone uploaded on July 2nd. So we were getting data all the way through till then, and we didn't want to get the data and then have to keep adding to it. So we waited till that final upload, and then Juan came from Berkeley, and we had a meeting, and in fact, I think I have the backup hard drive in my office. Anyways, I can bring it over and show you all. But and then we couldn't actually attach the hard drive to anything because it required a special docking station. And Juan's like, "Where's your docking station?" And we said, "What docking station?" Anyway, so then we had to buy a docking station. Anyways, so this is how things happen. It's like, well, we just want to look at the data. So finally we have the data. And so then Troy was looking through the data so that we can start just figuring out what we're going to share out. A lot of people who uploaded data later, when you uploaded data, people, they realized they had the timing off, or they realized that the lat long was off, or they realized all sorts of things in their EXIF weren't quite right. So they gave us all that information, or you all gave us that information. So our next step is to find kind of the data that we can really work with, make sure the metadata is correct. And what did it take, Troy? Like 2 days to actually copy over the data that we have deemed to be the first round of data we're going to look at?
At least. I started it on a Thursday, and I know that it was done on a Tuesday, the Tuesday that I came back.
And that's just from a hard drive to another hard drive. That's not even like over wireless or anything. This is all wired. So we have a lot of data. And when you have a lot of data, it takes a lot of time. So I'm glad you're all very patient people. And if you're not, I'm sorry. So Troy has now copied over. Oh, right. And then it was formatted to only open on a Linux machine. And we have Linux machines, but our students are using them. So we had to kick off a student off of one of our Linux machine and have her read a textbook instead for a while. So anyways, these are the little inner workings of science. But meanwhile, Juan worked this summer with a student to try to kind of rotate the images that he had. So we have her talk that we're going to show at the end of this presentation, her presentation on her work this summer. So we thought you'd like to see that. And I just want to thank both Hannah and Troy for all their great work. Hannah with all our communications, and Troy for his nonstop running of code to try to sort through all of, how are we going to analyze all this data. So, and of course, all of you for continuing to show up and help us out and participate in this project. It's wonderful. Okay, so I think that's it for the data and Kaggle competition. So watch for another email from Hannah either tomorrow or the next day. We're just trying to see if NASA will let us put in first prize a particular statement or not. So if they don't tell me in 2 days, we'll just remove that. And then anyways, we'll remove that and come up with something else. Okay, those are for the prizes. All right, so the next, should I go to the next topic, Hannah? Any, okay. All right, so the next topic, um, so when Troy and I were talking about kind of anchoring on that prominence, we there was a question, does the prominence change over the course of the time when the eclipse is happening in Mexico to Vermont or Canada? Like, did it actually change? Did it go away? Did the sun kind of rotate with it out of view? And I said, oh, well, we can look in HelioViewer and see what happened to it. And so we went onto the NASA website where you can see all this great NASA data. And then we were making all these cool movies, and it took a while to figure out, but we did. And then I thought, the volunteers might really like this for their own purposes. So you could take your own data and look at the HelioViewer NASA data and compare and contrast and maybe make movies. And then you can pull apart the NASA movie and put in your own data with, anyway, so with that. So I'm going to show you how to do that and a few other tools. So before I start, would you please raise your hand if you've ever used HelioViewer or either the student version or the research version? Okay, great. Awesome. Okay. So first, wait, don't give that link yet. Don't go to that link because I'm going to start with the student version. Can you really remove it? Did
I
you
guess
really?
so. Maybe
Wow,
because I'm a host or a co-host or something.
that's
Every day we learn
cool.
something new.
I know. Okay, so you're going to go to this one first. Student.helioviewer dot, is it com or org? Let's see. It is .org. Okay. And I'm going to share my screen. So as you know, I might just take over your screen. You're going to hit escape. If you want to be doing this yourself, you're going to hit escape, and then that will allow you to make the window small. So this is a student version that NASA made. Some of our colleagues in the education world created, and it is used with high school students around the country. It's also really, really cool just for like what's happening on the sun today, because it updates every day. So it's just like space.com and all that stuff, but it's the actual data, and you get to make it the way you want it. And so you see on the left here, there's a scale button, so you can zoom in to whatever is being shown to you. You'll see here there's this Earth scale on the left, and as you zoom in, you can start to see the size of Earth. And so you can see that Earth and sunspots aren't so different in size. In fact, the sunspots are much bigger, really, mostly than the Earth. So you might have seen here. So that's one kind of cool thing just to think about. Now, this is a composite. If you look up here on the left, it says eruptions and CMEs. It shows the date and the time. It says newest, and then you can say time step. So right now, if we just wanted to look at eruptions and CMEs, so CMEs are coronal mass ejections, which are dynamic flows coming off of the sun. And so it's hard to actually see an eruption or a coronal mass ejection when you are looking at a static image. So that's why I wanted to do movies with you later, so videos. But like this might be a CME that's been going off. This might be, it's kind of hard to know. But if you go backwards one day, then you can see how these things have changed. And so, and this bright spot right here is a planet. All the dots behind it are stars. And this is actually a compilation of 3 different cameras on the SOHO satellite. So SOHO is orbiting our sun at an L1 point, meaning it's just a point of gravity where gravity is kind of stable between Earth and the sun, and it sits there and it's looking at the sun, taking measurements, and it has all these cameras. And what you can see is this outer camera is measuring, it blocks the photosphere and just looks at the outermost corona and the solar wind of the sun. And then this inner one is looking at the inner corona. And then there's this black spot, this blank spot where no NASA data in visible light. There's no NASA data for visible light in this region. And so that's where your photographs really help NASA, is to fill in this blank spot. And then we can see the sun. This is in a helium emission here in the center. So that's yet another camera. So there's really 3 cameras right now being put together in one. But with these 3 cameras, you can see kind of what's happening in the solar wind and the corona. All right, so that's one thing that you can do with this. You can keep moving back in time, and you can see how the planet moves relative to the sun. You can also see here, this is for sure a coronal mass ejection. And I know that because I know what they look like. And they look like these big bubbles. So these are electrical, they're both electric and magnetic, so electromagnetic. These are gigantic magnetic fields. There's electrical currents that create magnetism, and they're populated with solar particles. So mostly hydrogen, but you can find all the other elements that the sun produces, all the way up to oxygen. And the photospheric part of the sun is reflecting off of this plasma, and that's why you can see it. And it's more dense. So the brighter it is, the denser it is. That's the nice thing about visible light observations, is that there's a direct linear correlation between density and brightness. And that's another reason why your eclipse data is so valuable to us, is because knowing the density is such an important parameter when you're doing physics. The density, you can just think about, the density of air compared to the density of water. If you want to understand a system, and you think about the fluid dynamics in water compared with the fluid dynamics in air, or the temperature dynamics in water versus air, things are going to be quite different. And so we care very much about density when we're studying the processes on the sun. Okay, so that's pretty cool. We found maybe there's a coronal mass ejection. It looks like it might not hit Earth because it's coming off the side of the sun. So really the CMEs we're looking for are called halo CMEs, because they look like a giant halo. And I know we've had some CMEs kind of recently, and you can see like all these amazing different, oh, the image just got flipped here. But you can see all these cool, how the corona just really changes over the course of a day right now, because we're in solar max. Another beautiful coronal mass ejection there. And so that's just something fun you can play with. And then here's a giant one you can see right now. So that was the beginning of the CME. And here it is leaving the sun. And then do you see how it then expands and becomes this giant bubble? But it takes days for that to happen. So remember, you were taking data over, like 4 minutes. And these processes can take, they take place over days. So what you're helping us with is kind of what seeds some of these CMEs, or what seeds some of these changes in the sun. That's what the eclipse data helps us with. All right, so that's the big picture. So there's a little option here, which probably many of you who already have gone here already clicked on. So if you go to flares and active regions, now we have to zoom in, because this is all about what's happening directly on the sun. These images tend to be, not all of them, but most of them are iron images. So iron, if you strip electrons off of iron and you let it glow, you can take photographs of it if you're NASA engineers. And this is what they look like. So it's so wild to me that like we have images of the glowing iron on the sun. That tells you how hot the sun is. Like think of iron, when the metalsmiths are doing their metalsmith work, they're working with iron and it starts to glow, but it's not yet a plasma. Like you haven't removed any electrons from that glowing iron. But here you've removed up to 16 electrons out of the iron atom. It's just so hot. It's millions of degrees Kelvin. So this is an extreme ultraviolet light because of how hot it is. And so here you can see there's all of these flares or active regions, which just means they're very dynamic. So flares and active regions really mean something active is happening. A flare is just like a flare up with your car, a car flare. It has that flare up of light, and that's very different than a prominence. And so you can come in here and you can play with you can again go to the next day and kind of see. You can also see the rotation of the sun, which I also think is super cool because you can see the sunspots moving because they get kind of embedded in the structure of the sun. Okay, and then if we want to look at the magnetic field of the sun, then there's this cool physics phenomena that light, in the presence of a magnetic field, light actually splits. It's called a Zeeman effect, and that split allows us to measure north and south magnetic poles using light. And so that's what this picture is. It's a picture of the north and south magnetic poles on the sun. I forget which is which, but the dark is either the north or south, and then the white is the other polarity. And so you can kind of compare the magnetism of the sun with these active regions. And you'll see that the more active regions you have is where you have higher concentrations of magnetic fields. If you look at the coronal holes, so these are areas where you don't have a lot of magnetism kind of popping out of the sun. So that's why they're called coronal holes. They're cooler, they look darker, but they also have the plasma that comes out of coronal holes are moving much faster than the plasma that comes out of the active regions, which is counterintuitive. And it's still a big question, like, why is that? Of course, we have theories and ideas that are being modeled, but the solar Parker
Probe.
what's that? Thank you. I think Hannah's going to
Parker Solar Probe.
the Parker Solar Probe. Yeah, NASA's Parker Solar Probe is in December going to be the closest of its closest approach to the sun. And part of the whole heliophysics big year is that journey. And one of its missions is to really understand why things are coming off the sun at all, and how that happens. And so they'll learn more about coronal holes, and already are. And then we have our white light sun, our sunspots. We talked a lot about the sunspots before on the eclipse. Okay, so that just gives you a little bit of a feel. It's very user friendly. The buttons are easier. You can turn events on and off. You can get back to the newest data very quickly. Okay, so I wanted to start with this because it's a pretty simple user interface. And I thought you all would like, this might be enough. Now you can go here every day. You can look at the sun in all the different ways, if you should choose to do so. Okay, so next I'm going to send you, but I'll stop for questions and then I'm going to stop sharing here for a minute. Okay, do we have any questions before we go to the Helio viewer? Yes, Spencer.
Was that a comment on the first image that you showed from that
Probably. There are tons of comets. And in fact, there's a citizen science project with SOHO that where you help them find the comets and track them. A lot of I don't know why I'm having such a hard time talking today. A lot of comets end up like running into the sun versus continuing around and back out. And so yes, so you can join that project, or you can just watch for yourself.
So you were talking about the coronal holes having a low magnetic field, and the question is it a low intensity or is a vector direction along the surface as opposed to in or out, or some combination of both?
Right,
And
it's a good
that's just
question.
curiosity on my part because E&M was like my worst um uh, I didn't flunk E&M, but pretty damn close to it.
Well, that's how I feel about engineering. So that's why we're a team. And E&M, I was like, I get this. But it's funny because like electrical engineering is E&M, but practical E&M. And I'm like, forget that. So the answer is that it's really because E&M is the magnetism on the sun is three-dimensional. And so these corona holes, they overall the kind of the magnetic field is less. So if we look at those, the magnetogram,
Yeah.
then that's where like there's just kind of no plus or minus. I mean, not plus or minus, north or south poles, right?
If you took the norm of the field to turn it from a vector into a scalar, you would just get to reduce the absolute value, if you will,
Right.
rather than the like because all those fields are vectors, so to
They are
speak.
all vectors.
Well,
That's
yes.
right.
Yeah.
That's right.
Okay.
And yeah, so they basically cancel each other. The currents in those regions have canceled themselves out, in essence. So
Yes, I love Hannah's comment.
I wonder what would happen if Magneto tried to fight the sun. I vote for the sun. We need
Laura would.
of course I would. We need a Zoom poll, Hannah. Sun versus Magneto. Okay, so all right, so we'll go to so if you now I want to show you how to make a video because the videos are so cool with the Helio viewer. So we'll go there and then so I'll just spend another few minutes on this. So Hannah, you can help push me along too. All right, so now we can go to that other link, helioviewer.org. And I'm gonna share my screen, but just hit escape if you're happy just navigating on your own. You don't want to watch me navigate. All of that's just fine. Okay, so did you see how I clicked on this and I hold my mouse button down and then I can move it around. So I can make this image go where I want to by clicking, holding, and moving. There's again an Earth scale. And then there's image timeline, events timeline on the bottom, but don't worry about that because what you probably don't have this data source open yet because when it opens, it's kind of hidden. So on the very far left, you want to click on this data source button so that you get all of these options. And I'm going to just take you through making a movie of a very specific thing, and then you can play as much as you want. So, I mean, of course, you can just play too. But for those of you who like to be stepped through a process, I'm going to step through a process for those of you. Okay, so we're going to go, our date is going to go back to April 8th. Okay, so why am I going to April 8th, you might ask? I'm just kidding. Okay, so Now that was 22. Why is that 20? Okay, so I went back to 2024. So the funny thing about HelioViewer is that it is not, it's really meant for researchers to go in and find things about the sun and use it with their research. And so you'll find that sometimes you'll think you changed the date. And then what happens is if the data doesn't exist for that date, it will take you to the data that does exist. And so it will change your date on you. So that's troubleshooting number one, is just keep checking that date because you might not be on the eclipse date anymore. Okay, so then we looked up the UTC for the eclipse, and it started, if I'm recalling right, at 16-hour UTC, and went through 19. So we're going to go down to 1655. Okay, so 1655. So one of the things with this, it's in universal time. You have to convert universal time. I mean, if you don't know universal time, you gotta, I mean, just Google when was the eclipse 2024 in universal time, and guess what? Google will tell you. That's the fastest way. And then you can hear, I need to move you all out of my field of view. Okay. And then what we're going to do is we're going to not, we're going to pick SDO because SDO's got just phenomenal data, just high resolution awesomeness. And so that's what you want for a video. And then we want to do AIA, which is one of the cameras. And we are going to pick 131, which is 131 angstroms. Now, just for context, an angstrom is about the size of an atom. So this is about 100 times the size of an atom is the wavelength. And this again is our iron. These are our iron lines. You are not going to make any difference. Don't click on that at this time. But actually, I don't think it was 137. That doesn't look right. It was 304. It was helium. Sorry, my bad. 304. We're doing the helium. See, because if I move this over here and then I zoom a little bit. So you can zoom a couple different ways. Up at the very top next to the word HelioViewer, there is a little zoom button. If you click on that, it will zoom. You can also scroll your third mouse button, or if you have a Mac fancy mouse button, you can use the scroll. So you're using the scroll here. So you can see that the Earth scale scales with my scrolling. So do you see this little prominence right here? That is the prominence that you all took pictures of or tried to take pictures of. Isn't it so cool? I just love it so much. Okay, so you can zoom in and really look at it, which is something that Troy and I did. We like zoomed in and looked. You can change the time, but I'm gonna have you do a movie. Okay, so then now we have it all ready to do our movie. So you have to get it all set up. If you want to move it over a little bit, you want your Earth right here. Maybe you want to scale it a little bigger because you want to see that. So the question we were asking is, does this prominence change much for the 3 hours of the eclipse? Or was it 3? I think it was about 3 to 4. So we're going to make a 3-hour movie. And now what you're going to do, you did all the data source. You're going to go up here to the right top of your view. And there is is it this one? No, all the way here. See how there's it says create a HelioViewer movie. It looks like if you put your mouse over it, it turns purple. It's got a square and a triangle and a square in a little icon. And if you click that, it will say generate a movie. And then you're going to click full viewport, just means everything I'm showing on the screen. So full viewport. And then you're going to make your duration 1 hour. 1 hour. I thought we were able to make it faster than that.
I think it only goes in hour increments.
Okay. I guess I was dreaming. Because we did 3 hours, but then we had a lot of frames. Well, we'll try. Anyways, I thought we'll try. So then we did, how many frames did we do here, Troy? Was it 30 or 15?
30 sounds right.
Yeah, I think we took anyways, you can choose. So right now we'll pick 30. And then if we do advanced settings, that's right. Advanced settings will allow us to then tell us how many. So we want to do 3 hours, or we could even do 4 here, 4 hours. Make sure the dates stay the same frame. You can make your size bigger or smaller. I'm just going to do original. And then we're not going to click either of these right now. And then we say, okay. And then I guess, okay, so it says your video is processing and will be available in approximately 5 minutes. You may view it at any time after it's ready by clicking the movie button. Okay, and it does take 5 minutes. While you're waiting, you can make a new movie with a different, so this is what we were doing with Troy and I. You can pick another wavelength, like 131. You see different things with this wavelength or this wavelength. I thought this was kind of cool because you've got this, it looks more like a shadow in this wavelength. You have absorption within that prominence. And so you can make another video if you want. Oh yeah, see here it doesn't have the duration. That's why. And that's why it's going to take 5 minutes. Okay, so here's another 5 minutes. All right, so now you'll see up here on the right, it says processing, and then it tells you how the percentage is. I know it's tiny, isn't it? It says processing 26% for the AIA 304 data, which is that helium data, and then we have our iron data 171 wavelength angstrom, and that's only processing at 2% right now. And so Troy and I were wondering if a lot of people start processing data at the same time, if the NASA servers like can handle it all or not. But that we'll find out what happens. It seems to be kind of stuck a little bit on this 26%. But and then you'll see that we'll get the movie here pretty soon. All right. So while we're waiting, are there any questions?
Yeah, I have a question.
Yeah.
Can you hear me?
Yeah.
How did you get to that data sources tab? I don't see that.
It's very hard to see. You toggle, do you see how it's on the very far left? And there's like a tiny little tab on the left. Do you see it there?
No, I don't see the tab.
Let me
Top
Could you still
left.
be on the students page, Tom?
Oh, that could be. Does it say student.helioviewer?
Right.
Right. So
Okay.
you have to now go to you have to type in helioviewer.org, which is
Oh,
separate from the student one. So
oh,
that's the research one is separate. Yeah. Thank you. Good job, Hannah. Nice debugging. We're going to put you on as one of our troubleshooting callers for Stamasis. Yes, we are. Too bad. You already did a good job. No good deed shall go unpunished, I hear. All right, so we're at 77% processing. We're getting there. Other questions? Other questions? Okay. Come on, processors. It seems to be processing both at the same time. Maybe I shouldn't have tried to do two movies. Well. Oh, I know what I can show you while we're waiting is that you can go to the YouTube channel then. Up here on the top right, it says movies shared to YouTube, and you can click on that. So there's recently shared movies. Whoops. And then, so Yeah, you can see kind of what people created recently. And so some of these, yeah, it looks like maybe our email spurred people to go to HelioViewer because there were no Eclipse videos when we came here, unless you went way back there to the time of the eclipse, and then there was one person who had made some. So I think that our email may have spurred people to go out and make some Eclipse videos. So you can look at other people's Eclipse videos and you can click on them or other videos. Like here's Mercury. See, I said it was a planet. And there was a comet. You saw the comet and you see the CME leaving. So now you can actually see the dynamic nature of our corona once you make a movie out of it. So I really wanted you all to be able to do that. Okay, so if we go back here, and then you can also see movies spanning in observation time. So these are movies other people made during the eclipse. And so some of these are the ones Troy and I made, but people made other ones. Okay, so now you see here up at the top, it says our movie is ready. Click here to watch or download. So what I love about this is you get to download your own movie. You get to make a movie and you get to download it. And then you can do whatever you want because it's NASA and you paid for it with your tax dollars. Yay! So here's our movie. So what we were wondering about is how much does this change over the time when we took the eclipse? Can we use it as an anchor? And we decided that it didn't move enough to be a problem, that we can use that as long as we can see it in our images. But you can see if you look carefully, you can see there's some cool little things happening, and you can see these like it's reaching out, and like these magnetic fields are evolving over time. Also, it's easier if you have good processing power on your computer. It's better to download the movies and watch them on your computer because I think just getting them through this application just doesn't work as well. Okay, so that's the first movie we made, and then here's the other movie that we made. And so then you can look at this one a little bit. We'll just see how it does. I'm assuming a bunch of us are on here, so it might be slowing us all down, which is totally fine and exciting, in fact. We always love when we slow down the NASA servers. It's one of our goals in the outreach world.
You're welcome, NASA.
No, they love it too, because it means that we're looking. So here you can see some of the changes in there even more. The absorption is it looks like it's breathing, like it's expanding and contracting and expanding. That's what I love about these movies too. You can see all like it's like bubbling away this chromosphere. It's so cool. Okay. Any questions? I think I am done showing you how to make a video in HelioViewer. All right, now this will all be recorded, so you can come back and watch the recording. Troy's gonna post it on our YouTube channel and our website.
We should also post the video Laura just made.
Oh yeah, right. I have a couple others we made too. So remind me to give those to you, Hannah. All right. Any questions before we go to our next agenda item, which is a little talk? Okay. Hopefully that was fun. Okay. So I think Troy sent me the video link to, oh, well, maybe you're posting it now. Thank you. Perfect. Okay. So I'm gonna share this. Oops. That didn't work. share. I have to click share sound, optimize for video sharing. Share. All right, so this is what Juan's been doing over the summer to try to get us closer to analyzing this data. Are y'all ready? Okay.
This is my NASA internship by me, Lillian Hall, and my mentor, Juan Carlos Martinez Oliveros. What is an eclipse?
Okay, can you hear it okay?
Mhm.
It's loud enough? All right.
A solar eclipse is when a planet's moon passes between the planet and the sun, casting a shadow partially or fully blocking out the sun's light. Facts about eclipses on other planets. Jupiter has large moons, making solar eclipses common. When Saturn's natural satellites pass in front of the sun, solar eclipses may happen. Mars has 2 small satellites that barely make an eclipse but can cast a partial shadow while blocking out the sun. Solar eclipses can happen in numerous exoplanets outside of our solar system, and eclipses cannot occur on Mercury or Venus due to lacking the natural satellites. Partial versus total eclipse. Total eclipses can only be seen from a certain site and last a couple of minutes, making it difficult to track the time variation of the corona. Partial eclipses are easier to study because it can be viewed from several places. Partial eclipses are long, and several scientists gather to record the time variation of the corona changes. Total eclipses last 10 seconds to 7.5 minutes. And then I read an article about solar coronal and polar jets observed during the 2017 solar eclipse. They were initially observed in polar coronal hole regions, studied with soft X-ray and extreme ultraviolet. Jets can escape from the sun in the solar wind, but the EUV and soft X-ray emission cannot be seen at larger distances. Several highly energetic jets have been proven to reach high altitudes, while smaller jets are not confirmed to reach such altitudes because of poor detection. The data gained from the solar eclipse was able to investigate the unseen behaviors of polar jets above the heights. And these were the scientific claims about the several jets. Polar jets contribute to polar solar wind. Energetic polar jets may escape the sun, while ordinary ones are less likely to. Some studies show that jets do not escape from the sun, they fall back to the solar surface. Standard jets cannot be seen in the images taken with SOHO, LASCO/Core 1, but blowout jets are seen. Blowout jets have larger widths than standard ones. And lastly, one claimed that the reason that the ultimate height of jets is not very clear is the limitations of height coverage in observations of the corona. And here are some images of the blowout, polar, and other type of solar jets in the sun. And then the Eclipse Megamovie. The 2017 Eclipse Megamovie was an opportunity that arose for people in the US to capture images of the total solar eclipse to align a movie of changes in the solar corona. Over 2,000 people submitted photos with a total of 50,000 images captured. The Megamovie scientists gathered, aligned, and processed the images to create high dynamic range images for the purpose of studying the solar corona. With the success of the 2017 Megamovie, the 2024 Total Solar Eclipse Megamovie is now in process. Now my project, The Goal. The Eclipse Megamovie in 2017 and 2024 include images taken without professional equipment. Because most of the photographers did not use tracking mounts, the moon and the suns move in time within the field of view. To reduce the data, the following steps were taken: aligning and recentering the images of the 2017 solar eclipse data using Python, processing the resulting images with the histogram equalization algorithm, and finding solar jets and flows in the solar eclipse data, which is ongoing. Now I'm going to get into the steps of image alignment. Image conversion and preparation. The images provided by the Megamovie, volunteers were uploaded in the native camera raw format. That is a binary file with non-compressed data and all camera metadata. In Python, using the model copy, the images were uploaded. To convert the images and prepare them for further processing, the following was made: converting images Python objects to NumPy arrays. Convert NumPy arrays to grayscale. With this, we changed the images from a 3-color multidimensional array to a 2D array, which is easier to manipulate. ECC algorithm setup. The Enhanced Correlation Coefficient ECC image alignment algorithm estimates the geometric transformation between the input and the template image as it returns the warped input image, which must be close to the template one, as it is shown below. The estimated transformation is the one that maximizes the correlation coefficient between the template and the warped input image. In our code, we define the motion model, initialized warp matrix as an identity matrix, and specified the parameters for algorithm. And then the image alignment step. Apply ECC algorithm to align image 2 gray with image 1 gray, and use CV2 warp affine to apply warp matrix to image 2 gray, producing image 2 aligned. And then computing and visualizing image difference. We implemented a code routine to highlight the difference between image 1 gray original and image 2 aligned by computing pixel differences. Here we can see the apparent motion of the image center and when possible its rotation. We highlighted the difference between the aligned image and then the preceding aligned image. Since the sample data set from one station, no changes will be visible and therefore this box will be empty. And here's a picture of the aligned images, and as you can see, the aligned image was converted to grayscale and was centered. And then image histogram equalization. Histogram equalization adjusts the intensities of the image so that the histogram of the output image is approximately flat. This enhances the contrast of the image. Filamentary structures in the solar corona are faint, and using imaging techniques like histogram equalizations help to detect changes in the coronal structures. And then lastly, we transformed the polar coordinates. To better study the sun's coronal structures, we transformed our eclipse images XY coordinate to radius angle coordinates. This conversion allowed us to analyze radial variations, study changes in coronal brightness and structure as a function of distance from the sun. It identifies symmetrical features, easily detect and quantify features with rotational symmetry, such as coronal streamers. It enhanced visualization, creating a visually striking polar plot that highlighted coronal details. And here's an example, and as you can see, it highlighted the coronal structures, which makes it easier to detect the changes. Thank you.
Great job.
Well done.
Laura, could we have a explain like I'm 5, what she was
Yes.
talking about?
I know, she's a teenager, isn't that crazy? Yeah, so she basically what she did is the idea was to apply a process to images to just see if it was rotated and you subtracted them, then you would see something because they wouldn't look the same. And so you could, like, in principle, if you had two pictures that are of the same thing, you just, let's say you're trying to rotate it, you rotate until there's the least amount of leftover pixels left, right? So you're trying to get it. So she showed like a perfect match would be a blank page because they're perfect, and every pixel subtracted from another pixel gives you 0. So you have a 0 everywhere. So that would be if you had like 2 rotated pictures of the same thing. And so you can use that first algorithm she talked about for both aligning and rotating. And then the second one she talked about was just flattening. So I think a lot of you who do image processing, you use other, you use Adobe Photoshop or other tools to flatten your images. So there's just a mathematical way to do that. So that was the second thing she talked about doing. And that just helps us pull features out. And then the third thing that she was describing, what was the third thing? The third Oh, polar. Oh, yeah. So that's something that it's so fun because Juan and I talked about doing this in 2012, because in the aurora, when you're trying to study the aurora, people do this too. They're called kiograms. So if you have a three-dimensional system, sometimes you want to map it in a two-dimensional space. And then sometimes you also want to just look at time variation in a two-dimensional plot. But so you first want to kind of flatten out your map of the corona. So that was the last thing she showed. So just like you can take a globe, right? If you have a globe of the Earth, then you flatten it on a map. That's basically, and then you can flatten it on a map in two different ways. You can flatten it so it just kind of fits a, a square or a rectangle, or you can flatten it so it has all those weird curves, and so it's more accurately representing the space between the places. And so what she was showing is if you pick the polar alignment, and you flatten it like you saw at that last picture, it's more like flattening a map, just completely on a rectangle. So you're not keeping the accurate distance between dots, from a geometric perspective. But when you do that, as you know, when we do that with maps and you look at the poles, right, like the Antarctica or the Arctic, you can see things they're much bigger. Apparently, they look bigger on your map because you've stretched them out. So doing that, just that mapping from, and it's actually literally in math called mapping. You're mapping from one coordinate system to another coordinate system. When you do that, you can then focus on a different part of your data. And so that the other thing you can do once you have those maps is then you can take one piece, let's say one streamer, where we're trying to find jets. So that means things are going to move from the sun out away from the sun. And so we might take like one plume, one area, and then just map that plume in time across our x-axis. And so if we have those plots, then we can chop them up over time and then make a plot of those. So that's where we're headed with that analysis. Yes, conformal.
Super cool.
So we have not been idle. I've been busy, and I'm glad that you all are always asking, well, what are you doing? What are you doing? Because then we're like, yeah, what are we doing? Oh yeah, we should show them this. Yeah. All right. Well, we're over our 6 o'clock time, but if you have any questions, I can stay for a few more minutes. Any questions on Lily's great presentation? Okay. All right. Well, I hope that you all have fun with making your own Helio viewer videos. And if you want us to, share them in Discord, if you have a really cool one that you think is deserving of a blog post or something, we're happy to post that. I'm saying for Hannah, send them to Hannah.
No, that sounds fun. Yeah.
We'll make blog posts out of your videos.
You guys all have my email.
Exactly. All right. Well, it was great seeing y'all. Thanks for coming tonight.
Thanks, everybody.
Thanks again, all.
Good to see you.
Recording off.
Right. Did the recording go off yet? Oh no, stop.